Let's practice computing the maximum efficiency and maximum work gotten out of a power cycle. So we're given that there's a power cycle operating between two reservoirs, and the temperatures we're given are 500 Kelvin and 300 Kelvin. Furthermore, we're told that there are 12 kilojoules of heat energy delivered from the hot reservoir to the system. The schematic picture that you should have in mind immediately upon reading this description is that of a power cycle, where remember, heat energy is transferred from the hot reservoir to the system transfers heat energy away into the cold reservoir, and of course exerts work on its environment so that you get power out of your power cycle. We can go through and label the temperatures, so T sub H, that stands for T sub hot, that has to be 500 Kelvin, likewise the cold reservoir has to be Tc equal to 300 Kelvin. Now from the description, we're also told that we get 12 kilojoules of heat energy from the hot reservoir. That's just the value of Q sub H, that's 12 kilojoules. Now remember, for any power cycle, we know that the efficiency of the power cycle eta is given by the ratio of the work done by the cycle divided by Q sub H, so the heat transfer from the hot reservoir. Remember, both of those are assumed to be positive. Eta should be between 0 and 1. Okay, but from the second law of thermodynamics, we're also given an expression for the maximum efficiency you can ever have with a power cycle. That's 1 minus the ratio of the cold temperature to the hot temperature of the two reservoirs. So we'll use both of those expressions in this problem. Let's start by computing the maximum efficiency of a power cycle with these two reservoirs. So eta max is just 1 minus Tc over Th, and we can put in the values. It's pretty straightforward. The only trick is making sure that you work in Kelvin so that that ratio is sensible. You do that, and it's 1 minus 0.6, which is eta max of 0.40. Alright, great. So that represents the maximum efficiency that you could ever have with any power cycle attached to these two reservoirs, and only these two reservoirs. So now let's compute the maximum amount of work that we could ever get out of this power cycle attached to these two reservoirs. Well, that's just assuming that the actual efficiency eta equals the eta max value that we just computed. So if eta equals eta max, well, we know the expression for eta. It's W cycle over QH, so we're just saying that that ratio is equal to 0.40. Basically, we built a power cycle that somehow lived up to its full physical potential. Now we can just solve for W cycle, because we know Q sub H, right? Q sub H is 12 kilojoules for this particular power cycle, and we just multiplied 0.4 times that value. So 0.4 times 12 kilojoules gives us a maximum amount of work delivered by this power cycle of 4.8 kilojoules. So if you really build your power cycle well, somehow you achieve maximum efficiency. Never mind that it's tough to actually do that in real life. The most work you could ever get out of this power cycle would be 4.8 kilojoules.